All right, welcome to Oceanography Online. We're going to do the best we can. I posted this PowerPoint presentation on the web, but this is going to be a narrated version that might help some of you out. I can highlight a few points. So we're going to first talk about general circulation of the ocean, and there are two types of surface or of ocean currents. There are the surface currents, which is the movement really of about the upper 1,000 or so feet of the ocean. And then there are the deep currents, which is pretty much all the other movement of water in the ocean. And the deep currents really, we focus on the water moving up and down. So how it gets down to the bottom and how it makes its way back up to the surface. But there are currents kind of shifting water around below the surface, and all of those really technically will be the deep currents, and that will be the next slide presentation that I post. So what I really want you to focus on in this chapter is what makes the currents move, and then what do the currents look like. So we split it into drivers, and then we'll look at some pictures of exactly what happens with respect to currents. So for the surface currents, the primary driver, number one, top of the list, is the wind. When we look at global air circulation, which we discussed back in Chapter 8, and I would encourage you to go back and kind of look at those global wind patterns in Chapter 8 to kind of understand this. There are two sets of winds that we're especially interested in for surface currents. The trade winds, which you can see in the middle of the diagram here, moving toward the equator, and then the westerlies, which are in the northern and southern latitudes. They're blowing roughly from 40 towards 60 degrees north and 40 to 60 degrees south. You'll notice the trade winds blow generally from east to west, and the westerlies blow from west to east. So, what is the effect of the trade winds? Well, the trade winds push the water to the west. So if we go back to that previous slide, we can see along the equator that's going to move the water from the right to the left along the equator, or from east to west. And then there are some other factors that come into play. So also going back to Chapter 8, you remember we talked about the Coriolis effect. And the Coriolis effect is going to cause that moving water to turn. In the northern hemisphere, it will turn to the right, and in the southern hemisphere, it will turn to the left. If we go back to this slide, you'll notice that the wind moving along with the equator toward the west, if you're north of the equator, you're going to be turning to the right and headed slightly to the northwest. The next thing that we have is the land. So if we go back to that slide again, you'll notice also as you're trying to go to the west along the equator, you run into South America, and at the same time you're going to turn either left if you're in the southern hemisphere and go down toward the south, or right in the northern hemisphere. So you can see how a combination of the Coriolis effect and the location of the land is going to cause this moving water to turn. We go back to our third driver that's listed here, and that's thermal effects. The other thing to know is that warm water expands and cold water contracts. And this results in the water near the equator expanding and producing a higher sea level. Water near the poles contracts, giving us a lower sea level. And when you put all of these effects together, you end up with a hill in the ocean. Now, this particular slide, which is a figure from your book, shows you the hill that forms in the North Atlantic. So this forms off of the east coast of the United States. You can see it's a little north of Cuba. There is a hill of water produced by the wind and the Coriolis effect that's pushing the water in that direction. The land is blocking the flow, and the thermal expansion on top of that causes sea level to rise. So that is a hill of warm water, and you'll notice it's located off the coast of Florida and Cuba. Once we have a hill, and you can try this at home, if you try to make a pile of water, that doesn't work very well, and gravity will then pull that water downhill. Now, it's difficult for the water to go back where it came because the wind and the other drivers are pushing it up. And so the tendency is for the water, in this case, to flow toward the north along the east coast of the United States. And so it creates a strong current that's called the western boundary current. And the western boundary current is located along the western side, in this case, of the Atlantic Ocean. This particular western boundary current is called the Gulf Stream, and it takes warm water from the area around Florida and Cuba north, and then of course the Coriolis effect is going to cause it to turn right, and so our western boundary current will then become a current that travels across the North Atlantic Ocean and takes that warm water over to Great Britain, which you can see on the upper right. So this is the beginning of what we call a geostrophic gyre. And the two currents that we spend the most time discussing on the geostrophic gyres are the western boundary current, which we just mentioned. It is a narrow, deep, fast current of warm water. I should have added warm water to that. And it is along the western boundary of an ocean basin. In the picture we have here, it is the Gulf Stream. The western boundary current then transitions into a transverse current. Here it's labeled the North Atlantic Current, which takes that warm water over to Europe and Great Britain. Once it gets there, the Coriolis effect and the winds cause it to turn. Also, the presence of Europe cause it to turn to the right. It becomes the Canary Current. And you'll notice by the way they've drawn the arrows here, the Canary Current is much wider. So the eastern boundary current is what the Canary Current is. It is cold, it is shallow, it is broad, and it is also slow. And it takes the water back to the equator, to our second transverse current, which is an equatorial current. And you'll notice that is the one that is created by the trade winds, and it starts the cycle all over again. This is another drawing from your book, and this just shows you the western boundary current, again, deep, narrow, warm, very strong current, and then the eastern boundary current, in this case the Canary Current, is broad, shallow, cold, and relatively weak. When we look at all of these currents together, we find that there are 5 geostrophic gyres in the ocean. The North Atlantic gyre, which we just looked at, has a counterpart in the South Atlantic. And then there are North Pacific and South Pacific gyres. And then there's one gyre in the Indian Ocean because, of course, the Indian Ocean is only in the southern hemisphere. So that's why we only have one gyre there. There's a little bit of Indian Ocean in the northern hemisphere, but not enough to allow for a gyre. One of the things I would point out on this map is the Indian gyre is kind of split in half because of where they cut the map. The other current that some people might recognize is the East Australian Current. It is a western boundary current, so it's narrow, deep and fast in warm water, and that is the current that is featured in the movie Finding Nemo where Nemo's dad gets in the East Australian current with the turtles, and they go south to Sydney, Australia. And you can see how that would work. Again, a fast, narrow current, just like they depict in the movie, with warm water, which makes it kind of a little bit nicer for a fish like Nemo's dad. And you can see that as part of the South Pacific gyre. So there are other currents, so some more surface currents. One is what's called the west wind drift. And the west wind drift moves around Antarctica. And one of the reasons why this current is interesting, and we'll go to the next slide to take a look at it, is the west wind drift, or the Antarctic circumpolar current, which you can see along the bottom of the map here, is blown by the westerlies, but there is nothing to stop the water. Remember, we said that one of the important factors in our gyres is the presence of land, which blocks the water, prevents it from continuing, it kind of helps deflect it. And in the case of the west wind drift, we can see what happens if you don't have land to block the current. In this case, the west wind drift just continues to go from west to east around Antarctica. It's a cold water current, and it actually blocks the warm water that might come down from the western boundary currents, the East Australian current, the Brazil current, and the current that's on the west side of the Indian Ocean. You can see those warm waters are deflected by that circumpolar current. And that's one of the things that helps keep the climate in Antarctica so cold, because that warming effect of a warm boundary current from the western boundary current never reaches Antarctica. The second one listed here is the equatorial countercurrent. These are interesting, and they tell us something else that's going on. And they're actually in some ways paired with the undercurrents. So we'll go to the next, we'll go back to the next map and take a look at that again. You might remember that we have a hill of water on the west side of each of these ocean basins, and that gravity pulling water off of that hill is what helps to create the western boundary current. Well, that's not the only place that the water goes, because water is a liquid. It's going to find its way downhill however it can. So the equatorial countercurrent occurs because along the meteorological equator, which back in chapter 8 we called the intertropical convergence zone, is a place where the air is rising. So there's really no significant surface wind. And because there's no significant surface wind, some of the water can sneak back along the equatorial countercurrent where there is no significant surface wind. The other place where the water sneaks back is under the north equatorial and south equatorial currents. There's actually an undercurrent going back in the other direction, taking water off of that hill. And that'll have an effect in some places where that undercurrent hits an obstruction like an island chain. That slightly cooler water will come back up to the surface. So the last thing to mention about these currents is that they move energy around. And this goes back to what we talked about in chapter 8 again. And this is going to affect climates. So any place where you see a red current or warm water hitting a coast, it's going to tend to warm that area up. And any place where you see the blue line along the coast, it's going to give them a somewhat milder climate in a what would normally be a warm region. So this tends to move energy around the planet. And that's it for this narrated PowerPoint. The next PowerPoint talks about deep currents.